In the remote corners of the Chilean Andes, where winding roads carve their way to the peaks, stand the white domes of ground-based telescopes. This location, favored by unique atmospheric conditions, is considered one of the best on Earth for studying the depths of space. By the end of the current decade, one of these domes will become significantly larger than the rest. This colossal structure, nearly as tall as a 22-story building, will open its doors every night to allow 7 of the world's largest mirrors to begin their work. The Giant Magellan Telescope, GMT, whose construction began in 2015, promises to deliver images of the universe 10 times sharper than the famous Hubble Space Telescope, and even 4 times more detailed than those captured by the James Webb Space Telescope. The GMT's unique design integrates 7 modern telescopes into one giant instrument, which is set to become one of the 3 most powerful ever created. The launch of the long-awaited James Webb Space Telescope marked a new era in the exploration of the universe. In space, it will be joined by observatories such as the Nancy Grace Roman Space Telescope, with its wide field of view, and the European Space Agency's Euclid, whose primary mission is to study galaxies, their clusters, and the evolution of the universe. These instruments represent the next step in humanity's attempt to unravel the mysteries of dark matter and dark energy. Despite the advancements in space telescopes, ground-based observations continue to play a crucial role. Moreover, it is on Earth that cutting-edge astronomical observatories are currently being built, promising to elevate optical and infrared observations to an entirely new level. Astronomers always strive to view the faintest objects with maximum detail. However, about 20 years ago, it became clear that even 10-meter mirrors were insufficient for further scientific progress. Larger instruments, giant telescopes capable of collecting far more light than existing ones, became necessary. The principle is simple: doubling the diameter of the primary mirror quadruples its surface area, allowing it to collect 4 times more light. An observation that previously took 4 hours can now be completed in just 1 hour. Furthermore, image detail is enhanced due to higher angular resolution. This means that 2 stars appearing as a single object through a small telescope will be distinctly visible through a telescope with a larger mirror diameter. Observation time is critical, especially when obtaining spectroscopic data needed to determine the chemical composition of exoplanet atmospheres. This requires observing an object approximately 100 times longer than for direct imaging. Large mirrors optimize this process and reduce observation time. However, creating large mirrors presents significant engineering challenges. Increasing a mirror's mass leads to deformation under its own weight and the impact of wind. Therefore, the maximum size for a single, monolithic mirror is limited to approximately 8 meters in diameter. But the 3 giant super telescopes of the future, set to begin operations in the next decade, successfully overcome this problem. The extremely large telescope, ELT, currently under construction in Chile, and the 30-meter telescope, TMT, planned for Hawaii, will be composed of numerous smaller mirrors working as a single unit. Similar to the James Webb, each segment will be mounted on a structure with motors that align them to form a cohesive mirror. This design is expected to achieve primary mirror diameters ranging from 30 to 40 meters. The Giant Magellan Telescope, being built at the Las Campanas Observatory in Chile, has taken a different approach. Instead of one large 8-meter mirror, it combines 7 such mirrors within a single observatory. Visually, it will resemble a flower with a central mirror surrounded by 6 petals. At first glance, the telescope's design might raise questions. Will the large gaps between the mirrors interfere with deep space observations? The round segments do not form a continuous surface like those of the James Webb, nor are they tightly packed, with a distance of about 30 centimeters between them. However, it's crucial to understand that astronomical photographs are not direct reflections from the primary mirror, as in a conventional mirror. Instead, the mirrors collect and focus light. Each of the Giant Magellan Telescope's 8-meter segments forms a complete image of the object, and these images are then superimposed to increase overall brightness and improve resolving power. The secondary mirror also consists of 7 segments, each corresponding to a specific segment of the primary mirror. light from one of the 8-meter mirrors always reflects to a particular segment on the secondary mirror. Equipped with an adaptive optics system, the secondary mirrors align and concentrate the light before it reaches the scientific instruments. In this way, all 7 segments function as one monolithic mirror with a diameter of just over 25 meters. Despite the presence of gaps, such a mirror can gather enough light to reveal the universe in previously unseen detail. What discoveries can we expect from this telescope? Will it be able to peer into the most distant corners of space and unlock mysteries that have remained inaccessible to humanity until now? We will soon find the answers to these questions. For the entire complex system to work flawlessly, 7 perfectly shaped mirrors are required. The optical design of the Giant Magellan Telescope, GMT, is based on the Gregorian system, which differs from the more common Cassegrain system by having both concave primary and secondary mirrors. Light, after reflecting off the primary mirror, is focused in front of the secondary, and then refocused onto the scientific instruments. This design ensures sharp images of objects across a wide field of view, and the concave secondary mirror simplifies instrument calibration. Furthermore, this configuration is ideally suited for adaptive optics, which compensates for atmospheric turbulence. The fabrication of a 20-ton glass mirror with a precise shape is an extremely complex engineering task. The only place where this is possible is the Richard F. Karras Mirror Lab at the University of Arizona in the United States. Beneath the university stadium lies a giant spinning furnace where mirrors for the world's most powerful telescopes are created, including the Large Binocular Telescope in Arizona, the Magellan Telescopes in Chile, and the Vera C. Rubin Observatory with the world's largest digital camera. To create high-quality mirrors, high-quality glass is essential. The Mirror Lab uses O'Hara E6 glass, known for its purity and resistance to thermal expansion. It is produced in Japan in large, handmade pots. After the pots are broken, the monolithic glass is cut into 4 to 5 kilograms pieces and shipped to Tucson, Arizona. There, technicians manually load approximately 20 tons of these glass pieces into the furnace. The heating and spinning process then begins. The furnace rotates for several weeks, reaching temperatures of around 1,200 degrees Celsius. The glass melts, acquiring a honey-like consistency. The rotation of the furnace allows the glass to maintain the desired shape. It is forced away from the center and rises at the edges, forming a concave parabolic shape. This technique avoids the need to remove tons of excess glass during the subsequent polishing stage. The mirror then cools slowly over a period of 1.5 months, after which the longest phase begins, polishing, which can take over a year. An ideal concave shape is suitable only for the central mirror. The other mirrors must have a potato chip-like shape to function as a single unit. Therefore, grinding and polishing require extensive time and effort. As a result, the initial mirror will become 3 tons lighter, and its surface will be polished to perfection, with irregularities within 20 nanometers. The finished mirror is then packed into a container and shipped to Chile, where the Giant Magellan Telescope will be located alongside the 2 existing Magellan telescopes. The Las Campanas Observatory is situated in Chile's Atacama Desert, one of the driest places on Earth. The dry air absorbs less light and does not promote cloud formation. Its remoteness from cities reduces light pollution, and the stable climate is favorable for mirrors sensitive to temperature fluctuations. It is no surprise that some of the world's best observatories are concentrated here, and another giant, the European Southern Observatory's extremely large telescope, is also under construction. By 2030, Chile is projected to host approximately 70% of the world's astronomical infrastructure. The southern hemisphere is particularly appealing for observations, as it offers a view of the galactic center and the supermassive black hole Sagittarius A*, the closest star to the Sun, Proxima Centauri, and its planets, as well as the Magellanic Clouds and other dwarf galaxies. Low humidity and high altitude are key advantages of the Chilean Andes. The Giant Magellan Telescope will be located on a mountain 2,500 meters high, which will reduce the atmosphere's impact on observations. The atmosphere, moving in an uneven flow, deforms light from astronomical objects, distorting the image. In the late 1980s, a technology emerged designed to partially mitigate the distorting effects of the atmosphere on the quality of astronomical observations. This system, known as adaptive optics, uses thin mirrors whose shape dynamically changes in response to air mass fluctuations. In the design of the Giant Magellan Telescope, GMT, this technology will be implemented on the secondary mirror, with each segment reaching approximately 1 meter in diameter and a thickness of only 2 millimeters. On the back of each segment, 675 electromagnets will be placed, capable of precisely pushing or pulling individual sections of the mirror surface. This will allow the mirror's surface to correct its shape approximately 2,000 times per second, compensating for distortions in the incoming light. For precise monitoring of atmospheric changes, a kind of beacon, a reference star of sufficient brightness, is necessary. However, the problem is that bright stars suitable for this role are found in only 5 to 10% of the sky. Therefore, modern telescopes create their own stars, using powerful lasers directed along the line of observation. The GMT will be equipped with 6 laser units that will cover the entire section of the sky intended for study. It is important to note that the Gregorian design of the telescope allows adaptive optics to calibrate the incoming light more effectively than in Cassegrain telescopes. This is because sensors can be positioned directly at the primary focus, located in front of the secondary mirror, which is not possible in the Cassegrain design. Furthermore, new, more sophisticated algorithms and miniature actuators promise to elevate the quality of the resulting images to a fundamentally new level, surpassing even the capabilities of the James Webb Space Telescope. However, it is worth noting that the James Webb Space Telescope is capable of detecting infrared radiation, which is inaccessible to ground-based observatories. It is specifically designed to observe extremely faint objects whose light reaches us from the time of the formation of the first galaxies. No ground-based telescope, whether modern or future, will be able to perform this task, as Earth's atmosphere is too bright and opaque for many wavelength ranges. In turn, the GMT compensates for this limitation with its exceptionally high resolving power, opening new horizons, for example, in the search for exoplanets. Overall, the scientific objectives for the construction of the GMT and other extremely large telescopes encompass virtually all areas of astronomy. However, particular emphasis will be placed on the study of planets and their characteristics. A key instrument of the observatory will be a powerful spectrograph, dubbed the Large Earth Finder. It will study planets comparable in mass to Earth and search their atmospheres for signs of life, so-called biosignatures. Specifically, astronomers hope to detect oxygen molecules, which accumulate in our planet's atmosphere due to the activity of living organisms. However, oxygen cannot be considered an ideal biomarker, as geological processes can produce significant amounts of this gas. Moreover, life on Earth thrived for billions of years before photosynthesis saturated the atmosphere with oxygen. Therefore, anaerobic bacteria, which dominated early Earth, could very well be inhabitants of other worlds. When considering Earth-like life, another important indicator could be methane, present in the atmosphere along with carbon dioxide. In addition to atmospheric analysis, the telescope will be able to obtain direct images of planets thanks to the presence of a coronagraph. Given the GMT's high resolving power,